Welcome. In this video we need to take a look at intervals of convergence. So the idea is we've got a function, we've got a Taylor series for that function, and we want to know for what values of x does the Taylor series converge to the function. What values make sense to plug in. There are several different methods for determining this. In the scope of this one credit course, we're really only going to look at one. I will talk about two. I'll talk about one that we're really going to work with, and then I'll mention another one just so you've been exposed to it, but really it's not what we're trying to do in this class. The main thing we're looking at is what's called a geometric series, and I like to think of this as the ice cream theorem. That was coined by a student of mine, and I'll tell you the story in a little bit here. So recall the Taylor series for 1 over 1 minus x. We just calculated this in the previous video. In fact, from the point of view of me recording, it was just a few minutes ago because I just finished recording that video, and now I'm recording this video. So here we go. 1 over x, the Taylor series is 1 plus x squared plus x cubed plus and so on, right? Just adding on bigger and bigger powers of x. Right? This is what's called a geometric series. And a geometric series is one where each successive term can be obtained from the previous one by multiplying by a constant. Right? So in this case, the way I have this written here, to get from one term to the next is multiply by x. Right? Actually starts from the very beginning. It's a very good place to start. Right? So 1 times x is x times x is x squared times x is x cubed. Each time you just keep multiplying by x and it gives you the next thing. You're adding up all of those things. So notice if x is, say, a half, the series looks like 1 plus a half squared plus a half. What the heck? Let me try doing this again. Yeah, that looks better. I can do powers of 2. 2, 4, 8, 16. I was doing evens there. That wasn't right. So 1 plus a half plus a quarter plus an eighth plus a 16th. If you keep adding those up, it adds up to 2. Now this may not seem immediately obvious, but think about, you have 1, okay? Now take another one and cut it in half and say, well, again, here's ice cream, right? Think about eating ice cream. I'm going to eat a whole thing of ice cream. Now I've got another one. It's like, I already feel like a glutton because I already just ate that other one. So I'm only going to eat half. They say, well, I'll just eat a quarter of what's left. Oh, I'll eat half of what's left. No, I'll eat half of what's left. I'll eat half of what's left. If you keep eating half of what's left, you eat a half and then a quarter and then an eighth and then a 16th. And eventually, you eat the whole thing. So you'll have a total of 2 that you've eaten. Okay. Yeah, and you can see if you plug in a half here, that 1 minus a half is a half, and then 1 over a half is 2, right? And do the reciprocal of a half, and that's 2. And so sure enough, the sum of these things agrees with that thing. It adds up to 2. On the other hand, we noticed in the last video, if I plug in x equals 2, that there's just no way this is going to converge. 1 plus 2 plus 4 plus 8 plus 16, you keep adding on bigger and bigger numbers. It's not going to come up to be something finite. It's always going to be getting bigger. According to the formula, that if you could do this, right, if this was equal, 1 minus 2 is negative 1, so 1 over negative 1 is negative 1. This should add up to negative 1. 1 plus 2 plus 4 plus 8 is negative 1. I don't think so. Okay. And don't let anyone tell you that it does add up that way. That being said, there is a fair amount of work that people have done, and I don't want to disparage them too much, at least those who do it rigorously, of what can we deal with these infinite sums that look like they diverge? Is there a way of maybe assigning them a value that might be of some use to us? And, there are some things that can be done, but it's not overly consistent. So I prefer to just say it diverges, right? That if you plug a 2 in for x, this series is not going to converge. It's headed off to infinity. And so this doesn't work. Now it turns out that as long as x is between -1 and 1, so each time you're multiplying by a number that's less than 1, somewhere between -1 and +1, so absolute value-wise is less than 1, that means each term is going to be getting smaller, right? Even if it's like 9/10, right? 9/10 squared is what, 81 over 100, and then you're multiplying by a number less than 1, so each successive term is getting smaller and smaller and smaller. Now, granted, it might get small slowly, but it's still getting smaller, and it turns out that it's enough to make it converge. It's curious if you look at 1 and minus 1. Let me just plug it in here. 1 is kind of funny. You got 1 plus 1 plus 1 plus 1 plus 1 plus 1. Clearly, that doesn't converge. It heads to infinity. If you plug a minus 1 in, you get 1 minus 1 plus 1 minus 1 plus 1 minus 1. It just keeps alternating between 1. So you have a plus 1 and then minus 1 to get you back to 0. Then plus 1 gets you up to 1. Minus 1 gets you down to 0. Plus 1 gets you to 1. Minus 1 gets you to 0. Plus 1, minus 1, plus 1, minus 1, plus 1. You keep bouncing back and forth between, as you look at the partial sums here, you look at 1, 0, 1, 0, 1, 0, 1, 0. It just does that. And it's kind of interesting that it's bopping back and forth between 1 and 0. But if you plug the minus 1 in for x here, 1 minus minus 1 is 2 in the denominator. And this says it should add up to be 1/2, which is exactly halfway between 0 and 1, which is kind of curious that this is bouncing between 0 and 1, and somehow this formula is saying this should equal a half. Yeah, there's some value to that. I still would say this diverges because it doesn't just settle down and approach arbitrarily close to any one number. Okay. So if x is between 1 and minus 1, this converges. Anything else, it diverges. Okay. Now here's the ice cream story. This is where I think of this as the ice cream theorem. Long ago, in a state far, far away, I was a young lad. And I want to say I was probably maybe 7th grade at the time. Maybe 6th grade, I don't know. But we were having ice cream one night, and Dad had gone out and bought one of those half-gallon blocks of ice cream from the local store. And he took out a big knife, and I forgot to mention there were 7 of us eating ice cream. There were 6 kids and Dad. I don't know why Mom wasn't having ice cream, but she wasn't. There were 7 of us. Dad took that big knife and he cut that block of ice cream into 8 equal pieces, and he gave each of us a piece. So there was 1 piece left. He then took that big knife and he cut it into 8 equal pieces, and he gave each of us 1 piece, and there was 1 left. And he did this maybe 3 times, and then there was mush left. But you could see the process. First you got an 1/8, then you got an 1/8 of an 1/8, then you got an 1/8 of an 1/8 of an 1/8. So an 1/8 and an 1/8 squared and an 1/8 cubed. And if you could keep going, it would just be the sum of 1/8 to the power, add them all up, right? And he then asked us the question, well, how much does each person get total? Now, he had shown me how to add geometric series up. So I was about to sit down and do this. I was going to say, this is the sum I want. 1/8 plus an 1/8 squared plus an 1/8 cubed, and so on. Now, if I multiply that by 8, so 8 times s, this multiplies 8 to be 1. This would cancel out one of the 8s on the bottom to give you 1/8. And then this would be an 1/8 squared, and this would be an 1/8 cubed, and so on. And it looks like then, if I do the 8s minus s, so this one minus that, I'd get 7s. But here, if I do the subtraction, I'd have 1, and then plus an 1/8 minus an 1/8, plus an 1/8 squared minus an 1/8 squared, plus an 1/8 cubed minus an 1/8 cubed, and so all of those would go away, and it'd just be a 1 left on the other side, and I'd divide and say that the sum of that original thing is 1/7. But before I could even think about finding a pencil, my younger sister, now if I was in 7th grade, she would have been in 5th, one of my younger sisters, said, it's all gone and we all got the same amount, so 1/7. It's like, to this day, I try to add up geometric series by thinking in terms of ice cream, right? Because it's so much quicker. And many years ago, I want to say 24 years ago, I think this was around 2000, I had a student who, when hearing that story, decided that he was just going to call this formula, this was the ice cream theorem, right? And you can see that it works because if you plug in 1/8 here and there, you've got the sum 1/8 plus an 1/8 squared and so on. So you got an extra plus 1. So bring that plus 1 over to the other side. So this side turned into an 8/7, but when you subtract 1, you get 1/7. And sure enough, 1/7 is the sum of all that stuff. So there you go, the ice cream theorem. Now, I want to take a look at something else and see if we can figure out what the interval of convergence is, right? That is, for what values of x does this converge? For this one we looked at already, the interval is from -1 to 1. We would say that that is centered at 0 and it has radius 1. Sometimes they talk about the radius of convergence. That's from the center out to the edge, kind of like the radius of a circle or a sphere. So here's a Taylor series, and I'm not telling you what function it comes from, but we ought to be able to figure out what its interval of convergence is. Because it turns out this is a geometric series. I can rewrite it like this. So 1 plus x minus 2 over 3 plus x minus 2 over 3 squared plus x minus 2 over 3 cubed. So the multiplier, the thing that's getting multiplied by each term to get to the next one, is the x minus 2 over 3. Geometric series with a constant multiplier, x minus 2 over 3. So it turns out that this will converge if that multiplier is somewhere between -1 and +1. Okay, so I need that x minus 2 over 3 in absolute values to be less than 1, which means that it has to be between somewhere between -1 and +1. If I multiply all three sides by 3, multiplying by a positive number will not change the direction of the inequalities. So -3, x minus 2. So -3 is less than x minus 2 is less than 3. And then you can add 2 to all the sides, and you get -1 is less than x is less than 5. So think about that interval from -1 to 5. 2 is right smack dab in the middle, and then you go 3 up and 3 down, and so you get from -1 to 5. The total length is 6, with 2 in the middle. The radius is 3. So I would say that this has radius of convergence 3. The interval of convergence is the x's from -1 to 5, right, with 2 right in the middle. And that's the way we are going to be able to tell intervals of convergence for this class. Really, the only ones we're going to ask you about can somehow be shown to be geometric series, and then you can figure out what that multiplier is and make sure that that multiplier is in absolute values less than 1, and that'll tell you which x's will converge. Now, there is a fairly standard test that is used for figuring out convergence, and that's called the ratio test. And I'm going to just to present it to you here. We're not really going to do anything with it other than present it and sort of show how it's related to the geometric series idea. And so if you're given a Taylor series, I'm calling it a power series, some constant times x minus b to the n, right, for n equals 0 to infinity. The ANs might be different each time for different values of n, but what I want to look at is a ratio of consecutive terms. I know that in a geometric series, the ratio of consecutive terms is always the same. It's always that multiplier that gets you from one term to the next. So if I do that for any series, so here's the n plus first term, and in the denominator here I have the nth term. If the x minus b's cancel out, most of them do, there's one left in the top. So I get a sub n plus 1 over a sub n times x minus b. And the theorem is that you can show that the series will converge provided that this ratio of consecutive terms is less than 1. Similar to, I know that's what it is for geometric series because I don't have to take a limit because this ratio is always the same. It's always just a constant times the x minus b. But this might, in this case, that might not be a constant. But as long as you can show this whole thing is less than 1, then you have convergence. Okay. And again, I'm not going to do that. We can do that for like the e to the x and the cosine x and the sine x, and look at the ratio test on those and take the limit as n goes to infinity and show that goes to for every value of x, you can show that is less than 1, and so it converges for all x. But, again, one last time, for the scope of this class, you don't really need to know the ratio test. I just want you to know that it's there. We'll be mainly looking at intervals of convergence with geometric series. All right, that's it for this section.